Hello everyone, welcome to lecture 5 of this course. In the previous lecture, we have discussed normal forms, call by name, call by value semantics, the Church-Rosser theorem and non-terminating computations. Today we are going to discuss how the if then else construct can be encoded in lambda calculus. We are also going to see how recursion can also be encoded in lambda calculus. And for this we need a combinator that is called Y combinator. So first we are going to see the design of the if then else construct. Recall that lambda calculus has only 3 constructs. A variable is a term, an abstraction is a term and an application is a term. This is an abstraction, this is an application. So in this language we do not have any constants like 0, 1, constant symbols 0, 1, 2 etc. We do not have the if then else construct in it, we do not have any data types. However, later we are going to see how some of these constructs can be easily encoded in lambda calculus. So the idea for coming up with that encoding is we would like to first understand the meaning of the function and try to write that meaning using this syntax that we have know for pure lambda calculus. And our goal for each one, whenever we are going to design different constructs, so design the lambda encoding of a construct from scratch. That means we are only supplied with these 3 types of, we may have variable, we may have abstraction, we may have application, nothing else is provided. From that we are going to come up with the lambda coding for different constructs we are going to study. So the if then else construct, we have, all of us are acquainted with this if then else construct. So we take an instance of the if then else construct. So say for example we write that if x greater than 0, then we are going to print x, else we are going to print x plus 1. So this means that x value is greater than 0, the value of x will be printed. Otherwise that means if value of x is less than or equal to 0, it will be printing x plus 1. Now this instance we can generalize this as if b, then c1, else c2. This b part that we have here, it is called a test. That means we are testing some, maybe it can be x greater than 0, it can be x equal to y, 2 variables we are checking whether they are equal, we are checking whether one variable greater than another and so on. It can be greater than or equal to, or x not equal to y, or any condition. So the idea here is these test conditions will always evaluate to true or false depending on the truth of this test. So we are testing whether this condition is true. So test or it is a condition. This condition will always evaluate to true and false. If it is true, then the statement or the command given at this position denoted by lowercase c1 will be performed. If it is false, then the statement given at this lowercase c2, we are going to, this c2 will be performed. So in this case, from the general structure we see here b is the condition x greater than 0. This is actual program that we have written, x greater than 0. Here c1 is print x and c2 is print x plus 1. So the meaning of the construct, we know that if b is true, then we do c1, the command or the statement given at c1, otherwise we do c2. Now if we look at these 3 things very carefully, that is b, c1 and c2, we find that these are the placeholders for the actual values. That means these are not, this b, c1, c2, they are not actual. This is not a, if I want to write a program with only if then else construct, then the actual thing, that means the instance will be something like this. So we can also have x greater than y, then y will be equal to x, else y will be equal to x plus 1. So this is an instance of this program. So b, c1, c2, what we have obtained, they are called placeholders for the actual values. So that means here b we are writing as x greater than y, c1 we are writing as y is equal to x, c2 is writing as y is equal to y assigned x plus 1. So these 3 placeholders b, c1, c2, we can now think of them as the 3 formal parameters of our if then else construct. So we denote this if then else construct by bold if, and we can now see that these are indeed the 3, as if this if then else is represented by a function if that has 3 formal parameters. These formal parameters will take on different values. B will be true, B will be false, C1 will be something like x is equal to print x, y is equal to x, C2 will be print x plus 1 or y is equal to x plus 1. So, this is the first thing that we have found. That means if the actual parameter for B is true, the result of BF is C1, that we know. The result for F was C1, F is true, the result of this is C1 means now it have to be C1 will be replaced by the actual parameter. That means whatever you are going to get by replacing C1 with the actual parameter, that is what we are going to obtain. That means when I write result of C1 means it is not C1, it is the C1 is a placeholder. So, whatever you are going to supply for C1 is what we are going to get. The same thing, if we are going to say B is false, then the result is what we are going to get when C2 is supplied with some actual parameter. Then we can generalize this if function as if B is true, we are going to select the first argument among C1, C2. Otherwise, we are going to select the second argument among C1, C2. So, it should be lowercase. This is lowercase. So, we write this way. It is lowercase. It is not capital C1, C2. It is lowercase C1, C2 because we are using lowercase. This is the placeholders. So, if B is true, select the first argument among C1, C2. That means what? That means we are going to get the actual parameters. Now we are assuming that we are passed. So, in C1 when you have passed the actual parameter here, so here argument here you can say this is the actual parameter. If this is the actual parameter, then it will be this is okay. Actually first argument among C1, C2. So here actually we should write, there I should write C1, there I should write C2, here I should write C1, C2. So, now the B is taking on a value true and you have two arguments C1, C2, already we have passed the values for lowercase C1, C2. So, then we have selecting the depending on the truth. So, B is true, we selecting the first argument, otherwise selecting the second argument. So, we get a structure like true oblique false, then we have C1, C2. So, if it is true, we are going to select C1, if it is false, we are going to take C2. So, our problem then reduces to selecting either C1, C2 based on the truth of B, true and false. So, how to go about with this? So, recall that we studied that first is a function that takes two arguments and returns the first one. This is called the first function. It takes two arguments, return the first. Similarly, second is it takes two arguments, return the second. That means if first Mn will be M and second Mn will be N. So, we know this. So, then we can say true will be our first, true will be equal to first and false will be equal to second. So, then if I write first C1, C2, that is true C1, C2, that will be C1, and if I write second C1, C2, that is equal to false C1, C2, that is equal to C2. So, thus selecting an argument from two arguments, we know how to do this and we have already studied that first and second. So, just in case of true, we are going to use as first and for false, we are going to use as second. So, now we are in a position to design the if. So, we will continue. So, first we have realized that there are three parameters B, C1, C2. Only thing that we have to do is the body, what will be the body of if. Now, when we pass the actual parameters, we get a structure like this. This we have seen. When we are passing the actual parameters for B, lowercase c1, lowercase c2, we get this one. Either it will be true or false, then it will be uppercase c1, uppercase c2. But these are obtained by replacing the placeholders with these values. For example, you have replaced B with true, you have replaced lowercase c1 with capital C1, similarly lowercase c2 with capital C2. Thus, we can write that if is equal to, there are three parameters. So, we write lambda B, lambda C1, lambda C2, they are lowercase because they are the placeholders, and our body is B C1 C2, B C1 C2. B is applied to C1 and the whole thing is applied to C2. So, this clearly means, that means when you have applied, we are going to get this. If all the parameters we have, actual parameters are passed, these lambda parts will go away. So, we are going to get true C1 C2 here, or it will be false C1 C2, uppercase C1 C2. This is what we are going to get. So, and that is the if construct. So this is our if construct. So we can write our if construct as this. So we write symbol that this means defined as. So if is defined as lambda b dot lambda c1 dot lambda c2 be c1 c2. So now we have to see whether it will evaluate correctly to what we want. So if true c1 c2. So we are going to pass. So c1 c2 this is what we are passing. So this will be true c1 c2. So we will parenthesize them. So this will be true. Then we have this one. Then we have this one. So now by beta reduction, first the b will be consumed with true. So we get lambda c1 lambda c2 true c1 c2. Now we have c1 c2. Again by beta reduction, this c1 is consumed by this c1. So we are going left with lambda c2 dot true. This will be c1 and we have c2. Again beta reduction, this goes away. So sorry, here it will be, here it will be, here it will be, here it will be, here it will be lowercase c2. No, it is not correct, it is not correct. Okay, c2, this is c2. Now this goes away, c1. Now you have c2. And true c1, c2, we know that this is equal to c1. So true c1, c2, that means true c1, c2, true c1, c2 evaluates to c1. Similarly, if we want to evaluate if false c1, c2, so then likely we are going to get here, if it is false, then these places will be written as false. So we can write this. It will be false, it will be false, this will be false. So this will be C2. So false C1, C2 gives us C2. So if our design that we obtained, it is indeed evaluating to the correct answer. So from now on, if represents this function written as lambda b C1, C2 b C1, C2. So C1 false also we have seen that it will be evaluating to the correct answer. Now, however, we have used a shorthand. So you see, we have written if we have written it as a shorthand like lambda b dot lambda c1 dot lambda c2 b c1 c2. This is a shorthand. That means we have used the minimal number of parentheses for writing this. So now we know how to obtain a syntactically correct pure lambda term. So put parentheses all around this. So we will have too many parentheses. So we will have this one. This will be parenthesized. So we will have this. So now again this is mn. So again this part will be parenthesized. So this is mn part is parenthesized. Now this is lambda part. So again this is parenthesized. Again this is another abstraction. So this is parenthesized. This is again lambda abstraction. So we have parenthesized. So this will be the pure syntactically correct pure lambda term. Well, now we would like to see how recursion is encoded in lambda calculus. As we have seen that if then else is not inbuilt within lambda calculus. So we have used the constructs of pure lambda terms and we have come up with a function corresponding to the if then else construct. Now we want to do it for recursion. So as before we have to see the meaning of recursion, and for this we need to look at some elementary ideas. So before we go to recursion, we recall that we have studied a term called self application. So self application is lambda x dot xx, and we have seen that when it is applied to itself, it is returning the same thing. That means it is called a non-terminating reduction, or it is a non-terminating computation that goes on forever. Actually, this is going to help us when we are going to design this recursion. So SA actually this will be very helpful for us. All the recursive encodings that we are going to do, somewhere this term lambda x dot xx or xx will be embedded as a subterm. So this will be very useful for us. So let us see once again what is SA. SA means, so we can rename it as u, and we can do beta reduction. So x will be taken away. So x will be replaced with u. So if that be the case, then lambda x goes away. So we are going to get in this x we are going to get lambda u dot uu, again we are going to get lambda u dot uu, by again alpha renaming we get lambda x dot xx, lambda x dot xx by alpha renaming. So that means we have got back to the old one. So SA reduces to SA. This will be very helpful for us when designing recursion. However, we cannot work directly with SA for defining recursive functions. So we need to modify this SA slightly. So we have lambda x dot xx. So we say SA prime will be lambda x dot f xx. So now we do SA prime. SA prime will be lambda x dot f x x, again this. But we want it as a closed term. Closed term or a combinator is one that has no free variable. That means here f is a free variable here. In SA prime f is a free variable. So SA prime f will be a free variable. So we want to make it a closed term. So we will make it bound. So that means we will have lambda f. So lambda f dot SA prime. This is SA prime. This SA prime is a closed term, that is called the Y combinator. So this was invented by Haskell, Brooks, Curry. So see how we have obtained the term Y from SA. So starting point was SA. We make a very small modification and we have got an SA prime. Then we did as before SA prime, and we have made that free variable bound and we got a combinator that is called a Y combinator. This will be very helpful for us to design recursion in lambda calculus. So we will show how to encode recursion using this Y combinator. It will be very helpful for us. Now before we go to discuss the combinator, there we have to see some properties of this combinator, Y combinator. So first we define what is called a fixed point, or it is sometimes written as a fixed point. So either way it is okay. So consider a function f. The fixed point of a function means that for some argument x, we have fx is equal to x. If fx is equal to x, then x is called the fixed point of the function. So for example, if fx is equal to x square, so fx is equal to x square, this function will look like this. We know that x square is, this is fx is equal to x square. That means at 0, the value of f of 0 is 0, f of 1 is 1, here it is 1, f of 1 minus 1 is also 1, but it is not, x is not equal to this x, f of x is not equal to x, f of x is 1 and x is minus 1. So minus 1 is not a fixed point, but 1 is a fixed point and 0 is a fixed point for this function. However, if you have this function fx is x plus 1, then we have to have something like x is equal to x plus 1. Now this is not possible. So then there is no fixed point for this function. Now when we move on to higher order function, everything is a function. Remember that in lambda calculus everything is a function. So that means x is also a function. That means f of p should be p. For higher order function, if x we are going to think of it as a function. So f of p is equal to p. P is called the fixed point of f. So now what is a fixed point generator? It is a function g that generates this fixed point for f. So there is a generator, given a function, it will give the fixed point for the function. That means g of f is equal to p, and we know that f of p is equal to p. If we eliminate p, that means if you substitute g of f for p in 2, so we are going to get f of gf is equal to gf, or gf is equal to f of gf. That means what, if you now replace g with y, we get yf is equal to fyf, and that is a property of a combinator that is called a fixed point combinator. So we will prove that indeed that y is a fixed point combinator. So what we have done, we have just replaced g with y, and we say y is a fixed point combinator. But however, we need to prove this, we will going to prove this. So this y, then the fixed point combinator is what actually gives the recursive function, it is not just any combinator, it is a fixed point combinator. So now we will see how to encode recursive functions in lambda calculus. So there is a theorem, so it is called a fixed point theorem. So this is given in Barendrecht and Berenson, 1994 in their paper Introduction to Lambda Calculus. So you can see that paper. So for all so it states that for all lambda terms f, there exists a lambda x such that fx is equal to x. That is part 1. Part 2, there is a fixed point combinator y is equal to this lambda f dot lambda x f x x lambda f x x such that for all lambda terms f yf by f is equal to fyf. This is what we have to show. So part 1 and part 2 we are going to do the proof. So part 1 we say let w be equal to lambda x dot f of x x f of x x. W is equal to lambda x dot f x x, and we have x capital X is equal to w w. Then we have x is equal to w w. So we can define, you can say this is defined. So this is, you can say lambda x dot f x x w. So this beta reduces to, so this is beta reduction, so it will be f of w w. Now w w is x, so that is equal to f of x. So what we have obtained hence is fx is equal to x. So this completes the proof of part 1. Now we have to do the proof of part 2. So we will do part 2. So we have yf is equal to lambda f dot lambda x dot f x x. Again we have lambda x dot f of x x, and we have this. Then you have f. So if you do beta reduction, this f goes away. So we have lambda f will be replaced by f. So we have lambda x f x x lambda x f x x. So it will be this one. So this part we name it say A. This will be helpful for us. Now we do beta reduction. So here this x will be replaced by this part. So then this lambda x goes away. So we are going to get f, and here this x is replaced by this one lambda x dot f of x x. Again there is x, so lambda x dot f of x x. So now you have this part. Now what is this part? What is this inside this f? Inside this f we have, inside this f what we have? Inside this f what we have? Lambda, if you have this one. So this part is actually, so this inner part is this thing. Inner part is this f. This part. That means this is A. This is inner part, we can write is A. Now this A is essentially YF. This is YF. This is YF, because YF we have come to this point lambda x dot fxx and lambda x dot fxx. So this we have obtained here. So this is FYF YA. So that means YF is equal to FYF. So this is what we have done. So we have proved it. So Y is a fixed point combinator. So this is how recursion is achieved. So you see left hand side is coming over again. So it is as if f function is calling itself with something. Again we can replace f with YF is FYF. So ever again YFF. So this is how recursion continues. We know how recursion continues, and this is what the idea about this Y combinator is doing. So this is the proof. Please see the proof. Let us go through the proof once again. So we have f we have applied here. So f goes away. So we have got this one. And now we can say this part is this. So now we do beta reduction. So then this will be, so if you do beta reduction, so then lambda x is consumed. So we get x will be replaced with this one right hand side. So you get lambda x dot fxs, lambda x dot fx. This part is already this A, this is your A. Now A is nothing but YF, so it is FYF. So we have proved lambda YF is equal to FYF. Now the recursive function. So we will consider for illustration the factorial function. So the factorial function we know it is factorial of 0 is 1 and factorial of n when n is not 0. That means f is equal to 1, 2 and so on greater than 0. So if n is 0, So we write factorial function, then we are writing like this in a programming language way. If n is 0, then factorial function will give us 1. Otherwise, that means n is greater than 0. So it is 1, 2, 3, 4 like that. So it will be n, we know n into n minus 1. That means factorial of n. So we say factorial of n is equal to n multiplied by factorial of n minus 1 when n is greater than 0, and when it is 0, factorial of 0 is 1. This we have written this way. So factorial of 3 will be 3 into factorial 2, that is 3 into 2 into 2, factorial 2 is expanded, 2 into factorial 1, factorial 1 is 1 into factorial 0, factorial 0 is 1, so we stop. So when we call factorial with n is equal to 3, it calls itself with n is equal to t and so on. So what we get? We get a structure like g within bracket g within bracket g, and as we have seen when we are doing yf, it was exactly like this. F calling a function, yf we got f of yf. So this chain goes on. So we are now trying to see the similarity between what we have studied for y combinator and normal recursion that we are used to. We have experience with recursion, so we know this. So let this be our goal. This is what we want to achieve. So this is in fact the meaning of recursion, that we have a function, it will call itself over and over again, and when you are talking about this meaningful function, that factorial function and things like some, so then we must have a basis of recursion, otherwise the recursion will not stop, it will go on forever. So somewhere it must stop. So we provide a basis of recursion. Okay, you go on, then you finally stop. Otherwise, it will be like SA. It will be an infinite reduction going on forever, because there is no basis of the recursion. So we will try to now define this lambda calculus. In lambda calculus framework, we want to write factorial function at a very high level. So we will be not now considering the elementary subterms that are there. So at a high level, we can translating our language into lambda calculus, and we are writing that n is a parameter, so it is lambda n. Now we have a if, we have already designed what is if. If has 3 things. So what we are checking? We are checking n is 0 or not. So if it is 0, it will evaluate to 1, and if it is not, then we are going to get f into n minus 1, f of n minus 1. Now this term is recursive. Recursive is not part of our calculus. So we have to do something else. So that now we assume that these terms these are called is 0, and 0, 1, they are part of Church numeral. That means we can design lambda encodings for each of them. Church numeral 0, 1, 0 is 0, n we can do. Also we can do multiply. Soon we are going to see how multiply can be encoded lambda calculus. And also n minus 1 can be defined by a predecessor function. That also we are going to discuss soon. So that means all of these elementary things, operations, can be written in a pure lambda calculus, as a term in pure lambda calculus. So assuming that to be the case, we first try to give a non-recursive definition of factorial. The non-recursive definition would be, you take f as a parameter. So then you make g is equal to lambda, defined as lambda g dot whatever was there before. Now what we have achieved, it is a non-recursive. This is non-recursive because left hand side thing is not appearing in the right hand side. Here f was appearing here, it was recursive. Now this will be our starting point. Given this, we claim that our factorial function can be found from this g. So our factorial function, now our third step will be factorial function, then we are going, f is this recursive, g is not recursive but it is not factorial, but now our factorial is f of yg. We claim f is equal to yg. That is f like this, which is recursive, because if you expand, we are going to get the f is there in this left hand side, right hand side. Now we want to compute f of 3, factorial of 3. That means now f of 3 means yg of 3, that is gyg of 3. This computation we want to see. So factorial 3 should give us 6. So let us see the working out or the computation of this one. So we will work those out in detail. So we will see yg3 is equal to gyg3. So this is m and p. So we will write gyg, this will come first, then this. So gyg we know it is g, we substitute, it is lambda f dot lambda n. So lambda f lambda n, then I am writing if is 0 n, it is 1, otherwise n multiplied by f of predecessor of n, and then we have yg. I am first doing yg, then I will do this 3, I will do this later. So then f will be consumed, replaced with yg. So we are going to get beta reduction. So lambda n if is 0 n 1 n times this will be yg. So we have to put in parenthesis, otherwise the meaning will be lost. So we are writing this way. Now we have to pass this parameter 3. So we will pass this parameter 3. So beta reduction again will give us if is 0 3 1, then 3 yg predecessor of 3. So now is 0 3, 3 is 0, this we know to be false. If it is false, then we will evaluate the second argument. That means we are now going to evaluate 3 times yg of pred 3. That means what we have to now compute? We have to compute 3 times yg of predecessor of 3 is 2. Predecessor of 3 is 2. So this part we have to compute, like yg 3, we will now compute yg 2. So how we are going to compute yg through? Yg 2, it will be straightforward as before. So here if you see, if we go through this one, so here it will be 2, here it will be 2. So then here at some stage we are going to get is 0 2, is 0 2. Is 0 2 is again false. So again we are going to get here 2 times yg of predecessor of 2. So that means now what we have obtained here? We have obtained 3 times 2 times yg of 2 is 1. This computation we have to do. So again we are going to pass 1 here. If you do carry on this computation, it will be is 0 of 1. Is 0 of 1 is false. So then this will come to 1 times yg predecessor of 1. So now here what we have obtained? 3 multiplied times 2 times 1 times yg of 0. Predecessor of 1 is 0. Now when we supply predecessor 0 here, so it will go on. Now it will be is 0 of 0. Is 0 of 0 is true. So that means we are going to get the first argument. First argument is 1. So that means this evaluates to 1. So now what we have? 3 multiplied by 2 multiplied by 1 multiplied by 2. This is indeed 6. So thus factorial function f is equal to, we have claimed f is equal to yg, and we have shown that it is indeed evaluating factorial 3. So f is a factorial function, then is represented as y. So we can summarize the discussion as that we have given a encoding of the if construct using lambda calculus, that is a pure, we have obtained a pure lambda term for if then else construct. We have also shown how recursion can be encoded in lambda calculus, that is a pure lambda term, and for this we have used a combinator called the Y combinator. So we stop here. Thank you for your kind attention.